Hello and welcome to 6034 Fall 2020 Recitation 1. We're going to be talking today about search, a problem-solving method that underlies many algorithms and methods implemented in classical AI and many more artificial intelligence applications still today and industry applications. It's a universal topic. And because it's so universal, and because it has existed for and been researched for decades, we find many types of methods. We'll be discussing a few of them here, and you'll see, at least in the ones that we choose, that many of these methods are improvements over the previous generation. Needless to say, today we'll be talking about different types of search. Some of them will implement heuristics, which is basically a rule of thumb, and we'll talk more about it when the time comes, but we'll be talking about heuristics, and given an example graph, we'll be conducting different types of search on it, so examples of different search algorithms. Without further ado, let's start with different types of search. I'm going to outline the different types of search, broadly categorized, into two categories. Let me start with the root node at the top. Let's say the root is all search algorithms. Then we can broadly say we have two classes: non-optimal and optimal. Now you may ask, what do you mean by optimal? And what we refer to, at least in the context of this recitation and this course, is algorithms that will give you the shortest path between a given start node and a given end node. So when you know the endpoints and you use a particular algorithm, it'll either give you a path that is guaranteed to be the shortest path between the two, or it'll find some path, if it can find a path. We'll talk more about that later. So the first category obviously is search algorithms that will not necessarily give you the shortest or optimal path. And within this first category, we have blind searches. Blind search algorithms are those that have no information about the environment or the search space in which you're conducting your search. I know it's a little bit redundant, but imagine yourself in a maze, and you were just dropped in there out of the blue, and it's dark, so you have no information to go on except the path that you're currently on and where you've been. And that's what we would say is a blind search. And the first two that come to mind are depth first search and breadth first search. And you heard about them in lecture, but roughly summarized, in depth first search, what happens is whatever new path you find is, let's say I encountered a fork in the road traveling this maze, then I would go down, let's say the left side, and then I encounter another fork in the road. Something like this. I took the left, so now I do this. And I have two options. I can either go back to the other side of the fork, this side, and expand further, or I can keep going deeper. If my philosophy is always go deeper first, that's depth first. If my philosophy is to go sideways, basically expand everything first and then go one layer deeper, that's breadth first. With that basic out of the way, let's add a third type of algorithm, and that is the British Museum. And generally speaking, the British Museum defines a generic class of algorithms. It's not one algorithm, but for the purposes of this course, we'll consider it one algorithm, and it does the following. It essentially looks for all possible paths within the space. It's as though you want to map the entire maze instead of finding your way through it. And it does so by brute force. There's no particular sophistication in how British Museum is done. Okay? And so, moving on, we no longer have any more blind searches. What we do have are informed search. An informed search is where you have some information about some heuristic information, let's say. And so far I've been using the term heuristics fairly broadly. And what I mean by heuristics is some rule of thumb. It's not guaranteed to give you the right answer, but it's a good rule to follow. For example, let's say that I was dropped into a maze and I'm trying to find my way out, and I know that the way out is very near a very humid area. Let's say the exit is on a swamp. Then a heuristic for me, as I try to find my way through the maze, is how many bricks with moss are on this wall before maybe I decide to go left or right at the fork I spoke about earlier. It's a good rule of thumb because more moss on the walls would be indicative of me being closer, but it's not necessarily true, especially not always. And so, going back to the tree, there are 3 different types of algorithms that rely on heuristics. The first is hill climbing. The second, beam search. And the third is best first. All right. We'll speak about those later in the examples. I'll elaborate how to go through each search algorithm. I'll move this around a little bit, or actually I'll zoom out so that I can talk about the optimal searches. And in reality, we have one optimal search and one with a caveat. I'll speak about the one with a caveat first, and that is, again, British Museum. And that's because if you map out the entire maze, going back to the maze example, you will find the shortest path, undoubtedly, because the shortest path is one of the paths that you've already found, thanks to British Museum. So technically, you will always get the best path with British Museum. It's just extremely inefficient, and it's a blind approach. There are more sophisticated and better ways of doing so. One of them, and the one we're going to cover in this course, is branch and bound, abbreviated B&B. And branch and bound has a couple variations. One of them involves the use of an extended set. Another one also involves, I'm running out of space again, use of heuristics. And then finally, I'll make a note here that the heuristics the heuristics used need to be admissible. In the next section, we'll talk about those. And now finally, if you do branch and bound, you include both an extended set and you include the use of heuristics, you get what is known as A star. And for A star to work and be an optimal search, the heuristics, instead of being admissible, need to be consistent. Now, I have a small table, or not small, but I have a table that we can begin to fill out with the different details, at least on the blind searches, before we move on to heuristics. I would like to cover the material that doesn't have to do with heuristics first, and then we'll move on and introduce the complexity of heuristics. So let's go first to discuss a little bit the blind searches. Okay, so we're looking at the table of all the search algorithms that we're going to cover today, or most of them. And I want to cover first the blind searches before we cover heuristics. For BFS, if I'm referring to the example of the maze at the beginning of the recitation, if I'm at a fork in the road and there are two paths, I want to explore what's at the end of each path, or at the end of each corridor, if you want to think of it that way, before going past any of the two corridors. Which means that the first paths or the first corridors that I see are the first ones I want to explore. First in, first out. That would make the BFS rely on a queue. So let's give it an X here. And then on the contrary, if it were DFS, depth first search, I want to explore what's down this corridor, and if I find yet another corridor in there, or two more, I'll want to explore those before exploring the first one on my other side when I encountered the first fork in the road or in the maze. So that would be a basically first in, last out, because new paths or new corridors, as I find them, I keep stacking them on to the to my to-do list basically, and so that's what we call a stack. That's what we'll be using in DFS. Now, I want to come to mind that for both of those, or for both of these in this course, and throughout the course of this recitation, I'll be talking only about queue, and instead I'll be talking about adding to the front or to the back of the queue, instead of using stack and queue, and you're relying on the subtlety between the two just to make things easier for people who are not familiar with that vocabulary. Okay, so when we go to the second row, or the second grouping going down, need edge weights and need heuristics, because we're doing blind search, we're blind both to edge weights and to heuristics, so those don't apply. Then there's no size limit on the agenda, there's no cost function, and then we go to the bottom. You may notice that I skipped British Museum because really it's such a unique case because of its brute force approach that it doesn't, many of the things in this first block didn't really apply. And now here at the bottom, we talked about earlier that British Museum will yield the shortest path, and in the case of breadth first search, I'm going to make an asterisk here because it will only find the shortest path when the edges are unweighted. So if you define a shortest path as the minimum number of nodes and edges traversed, then breadth first search will be the one to find it. However, all three searches are guaranteed to find a path if it exists, because they will keep running until they find one. Needless to say, British Museum just finds all of them. And now at the bottom, British Museum, again, just by brute force, it's the special case of the asterisk on the optional guaranteed shortest path. If the smallest number of nodes or edges basically is what you define as shortest path, then BFS will take care of it. Now, let's go back to heuristics. Give me 2 seconds until I can go back. Okay, there we go. First, let's talk about what admissible heuristics mean. And just to refresh your memory, admissible heuristics is what's required for branch and bound plus heuristics to work, or to guarantee you the optimal path, the shortest path. Now, what we refer to admissible heuristics I hope you can understand cursive, is broadly as a concept that it never overestimates. that means that the heuristic value, let's say I'm thinking of going from node A to node G. Instead of node A, let's say node S. Node S to node G. Let's say this path is 10. The length of the path is 10, but the heuristic value at S is 9. This is an admissible heuristic because the heuristic does not overestimate the length of the shortest path, assuming 10 is the shortest path. And the way we write it a little bit more formally is, let's write it this way. I'm going to use, after this one, a little bit more mathematical notation. It's not going to be precise, so if you're a mathematician, avert your eyes. So for each node, I, it needs to apply, hold for all nodes. In the set of nodes, you need to check whether the heuristic value between that node I and the goal node is less than or equal to the length of the shortest path as P of Ni and G. So referring back to the original example, had this been 11, the heuristic value, then this would no longer be admissible. Now, let's talk about consistent heuristics. And consistent heuristics are a stronger constraint than admissible heuristics. Consistency in heuristics, I want to write it out and then we can think through it together. It's just so much easier to write in cursive than individual letters. So this time I'm basically applying the admissibility of heuristics, that condition, on all pairs of nodes. In the previous one, the goal node basically was fixed, and I just checked all the other nodes in the graph versus one goal node. But now, I'm going to go for every pair of nodes. So Ni and Nj are going to be two nodes in my graph. I'm going to be iterating over all the pairs of nodes. So for all Ni in the set of nodes, for all Nj in the set of nodes, the absolute value of the heuristic value of Ni to some goal node minus the heuristic value of Nj to some goal node has to be less than or equal to the length of the shortest path between Ni and Nj. Missing parenthesis there. So I encourage you to, as an exercise, try to figure out how you can turn this consistent heuristic into, or how you can find a connection between the admissible and consistent heuristics. In particular, the admissible condition is a special case of the consistent one. And I already said more or less how they're related at the beginning of the slide, but I won't say any more so that I can leave this exercise for yourself. And this is a small proof of, or a small counterexample of something that I want to show you. So if we do the test for admissible heuristics, you just have, I'm going to do a small one, and then this should be done for all nodes. For the sake of time, I won't. but take my word for it that it should be admissible. Pardon me. So let's take the heuristic value of AB as an example here. So the heuristic value of AB is 0. The shortest path between A and B is 2, which means it's an underestimate that's admissible. And you can do that for all pairs. Because they're all 0, except one of them, which is 3, then they're always underestimates. In the case of AC, the shortest path between A and C is 4, which means it's still an underestimate. So that was an easy check that it's admissible. However, if we apply the consistency test, let's check for consistency between using A and C, or A and B, with C as the goal node. So let's check the absolute value of the heuristic value of AC minus heuristic value of AB. And that must be less than or equal to the length of the shortest path between, whoops, this is a mistake, not AB. This is, C is the goal node, which means it's BC. And then this has to be less than or equal to the length of the shortest path between A and B. Instead of writing out the full notation, I'm just going to write the shortest path directly. The shortest path between A and B is 2. This is 3 minus 0, so less than or equal to 2. It is not consistent, even though it's admissible. And it's important to know, because if a graph has consistent heuristics, it implies that the heuristics are admissible. However, if you know that a graph has admissible heuristics, that in no way implies that they are consistent. And the reason I bring this example up is because this is the consistency aspect is a manifestation of the triangle inequality, where if you have a triangle with sides A, B, and C, the length of any two sides must be greater than the length of the third side. That must always hold. And that's the basis of the consistency of heuristics. To continue with today's recitation, we're going to use this example graph, the backstory of which I'll read shortly, and we're going to go through the different algorithms that you saw on the table. Well, most of them, not all of them. And the backstory behind this graph, you can see it somewhat drawn on the iPad already, but just to make things a little bit more fun, Frodo Baggins, a small hobbit, has been tasked with destroying the One Ring to rule them all. To do so, he must travel from his home in the Shire all the way to Mordor. Following is the map of Middle-earth, where distances from one place to another are marked, and numbers inside each node indicate heuristic estimates of the distance to Mordor. So we're going to start with British Museum. So the information about heuristics and path and distances isn't really going to affect anything that we do, because we're just blindly extending every single path that we find. So I'm going to start with the Shire, or S, or start node. Typically we use S for our start node here. And I'm going to make three extensions. The convention, at least in 6034, is that we write from left to right the paths, or the nodes alphabetically, if they are letters, of course. So I'll write A, B, and C, and I'll follow the alphabetical standard, or the alphabetical ordering for the remaining paths. It doesn't, because it's British Museum, it doesn't really matter in which order you extend, as long as you cover the entire space. So I'm going to go about it by levels, just to be consistent in my way of extending these paths. So from S to A, I can go either to B, alphabetical order, or to M. From S to B, I can go either to A or to C. And then from C, I could go to B or to M. Then I extend one level further. And notice I want to bring your attention to something in particular. From S to A, I extended only 2 paths, but I could have had a third S node, right? But at least in the context of this course, we're not interested in paths or extensions that would lead to loops, so we typically just ignore them altogether. That's also why on this next level, I'm only extending one branch further. And now without further ado, from S to A to B, I can now go to C. From SAM, I can also go to C. Pardon me 1 second. There we go. SBAM, SBCM, SCBA, SCMA. One more round, and that should take us to through the full search space. And this should be M. B, it's just the node that's missing out of all of them. C, A, M, and then finally B. Now, that's the entire search space, but if we were given, let's say we were told, find the shortest path from the Shire to Mordor using British Museum. This would be this entire coverage of the search space needs to happen, but now you need to give a final answer. And what you do is you highlight the shortest path out of all the paths that British Museum gave you. And that would be this one. And that's it for British Museum. Now that we're warmed up from performing British Museum search on the map of Middle-earth, let's move on to more complicated search algorithms. The first one that we're going to do is the first one in adding heuristics to the search algorithm, and that's hill climbing. And hill climbing, I've noted right here, is DFS-like, and I want to point us to the table that we discussed, or that we started filling out with DFS, BFS, and British Museum at the beginning of Recitation. And that should highlight the similarities between hill climbing and depth-first search. And on top of that, it should give us a good hint of where to go, or a good hint of how the algorithm should go as we go through the search of Middle-earth, or the map of Middle-earth. Okay. So as I mentioned before, hill climbing is much like DFS, and a reminder that here in this recitation and in this course, we're using Q without any distinction between what a stack or a queue are. Q is the list of paths that need to be extended in breadth first search. The paths are added to the back of the queue. In depth first search, paths are added to the front of the queue, because the last one you saw is going to be the first one to be extended even further. In hill climbing, the same algorithm applies. Once you extend, let's say, node S into 2 more paths, those 2 paths are added to the front of the queue. So those are the next 2 to be extended, except before adding them to the queue, and this is where the difference comes in between DFS and hill climbing, you sort them by heuristic score. So whichever one has the best heuristic score according to what you want, then that one is the one that goes first on the queue. So we're going to mark and cross out here, use a stack, or in this case, we just add to the front of the queue, in other words. And then we start going down the list. Needs edge weights. Reminder that we're using only heuristics, not edge weights yet. So that's a no, but right at the bottom, needs heuristic, yes. Set size limit on agenda. That's not a problem, at least not yet. Uses cost function to pick a path to extend. In our case, we're using heuristics as the cost function, or we could use heuristics as a cost function. There is some metric that we're using to sort and choose the best path. And then at the very bottom, guaranteed to find a path if it exists. Yes, because no matter how bad or how good the heuristics are, if the path is not found, it will continue exploring until all the options are exhausted, or until the path is found. Now that we have that as a basis, we can go back. And if you've ever implemented a depth first search algorithm, this should be fairly familiar. But in case you haven't, then, well, we're basically going to go through it together. Okay, so at the start, I need to evaluate S, that's the Shire, that's our start node. And notational note here, when I am going to evaluate a node, or when I evaluate it and I perform the evaluation step, I give it a number here. That one indicates that was the first path extension or evaluation. And also notational note, I typically draw or add the heuristic score or path length, whichever is most relevant, to the bottom right. It doesn't need to be exactly this way, but I believe it helps me keep track of all the variables, because they're going to be quite a few soon. Okay. So I've extended S. Whoops, I need to change color. And that gives me 3 paths. A, B, C, and 3 new heuristic scores. 50, 4, and 7. Now, we're thinking, going back to the table, we have 3 new paths. We haven't yet added them to the agenda. First, we need to sort them. Reminder that when I again need to change color. Let me erase this first. There we go. When I evaluated this, darn it. When I evaluated this, this was my agenda, or my queue, sorry. My queue, and I popped it off, which means after when I put the number 1 here, my queue looked like this. And at the moment it looks like this. Now I'm going to proceed to sort these 3 new paths by heuristic score and then add them here. When I start sorting them, the first one to come is SB with a heuristic score of 4, then SC with a heuristic score of 7, and SA with a heuristic score of 50. Now, I need to, again, pop the next upcoming path off the queue, which is SB, which means B receives the second evaluation or the second extension in this algorithm. And again, I get 2 more paths. I see A and C. I'm going to write again the heuristic scores and 7. And now I need to resort. Allow me to erase this before it confuses anyone. There. Now, here comes an important subtlety. So I'm going to write on the side, my queue after I popped on 2, so this is between step 2 and 3, I'm going to make a cloud here, say this is step 2.5, in between the 2. My queue was the following, SC and SA. I get 2 more paths. They are SBA and SBC. And I want to add them to the queue. First I need to sort them by heuristic, and then I add them to the front of the agenda, which means the new queue is as follows. It's SBC, SBA, SC, SA. And I forgot, amid all the explanation, I forgot my notation of writing the next in line in red. There. Another thing I want you to note is that in heuristic is a score or an estimate. I'm going to say an estimate of how close one is to the goal node, which means that the heuristic score at A, at A here and at A here are the same. In other words, SBC and SC have the same heuristic score. SBA and SA have the same heuristic score, even though the path in one is longer than the other. Okay. And now to finish it off, I'm going to pop SBC off the stack. I extend C one more time. I get M with a heuristic score of 0, which means to my Q, I add SBCM, SBA, SC, SA. And now this begs the question, am I done? The reality is, no, I am not. And the reason I'm not done is because even though I've extended a path that leads to the goal node, a computer is blind to what the goal node is until you check that that is indeed the goal node. And the way you check is that this is the path of the goal node. This needs to be popped off the queue and extended. So let's say this is step 4.5. More or less, because it's once I pop SBCM off the queue, this is in step 4, so M gets a 4. Now, once I try to extend the goal node, that's when I am done. And so the reason I add the step 4.5 is because in order to be done, the queue needs to look like this. I'm gonna use 3 dots in the place of the path that was just popped. Right. This is the 4.5 is an imaginary step. It's for visual purposes. You don't need to draw it out so explicitly. But what needs to happen is that this M needs to have been extended or evaluated, because that's where the validation happens of, yes, this is where I stop because I've just found the goal node and tried, or by trying to extend it. And in order to return a final answer, then we circle the path that we found. And that is it for hill climbing. Okay, so let's talk now about best first search. In particular, let's talk about it in comparison to hill climbing, because so far in this semester, my previous experiences last year TAing, and also my own experience taking this course, best first search is one that lends itself really well to be confused with hill climbing, and including beam search, but really the crux of where our understanding is shown is knowing the difference between hill climbing and best first search. So let's go back to the table where all the search algorithms are, and let's start filling it out with the key differences. Now, hill climbing, to review or to recap, it takes, let's assume we are node S and let's assume you get 3 paths from node S. Those 3 paths are sorted according to heuristic, and then they're added to the front of the queue. Now for best first, what happens is first, obviously the start node is extended into 3 paths, but those 3 paths are added to the queue, and then the whole queue is sorted. So the first 2 rows, front of the agenda or front of the queue, back of the queue, don't really apply, but best first is the only one, at least in this group of informed searches, that sorts the agenda. And it doesn't really use path lengths, so we also need heuristics, and the heuristics here function as the cost, or work as the cost function. And then finally, because the only change from, I won't say BFS or DFS, the only change from hill climbing is that the whole agenda is sorted according to heuristic except the new paths. It means that eventually we'll end up exploring all the paths. So let's assume it doesn't find the path that we wanted from the start to the goal node, then it'll just keep going until it runs out of paths or until it finds it. So this it's guaranteed to find a path if it exists. Now let's go back and let's fill out the search algorithm. Okay. We start, as usual, with S. As a reminder, we pop from the queue. We evaluate. That's what gives it a 1 here. I'm forgetting my notation. This is a 0. And now, back in black. I extend again. And again, it's A, B, C. So far, it's similar to what we saw in hill climbing. And let me add the heuristics before updating the queue. Okay. And so far, it's going to, up to this step, as I write it, it's going to look identical to what we saw in hill climbing. But pretty soon, you'll see where the big difference is. So I'll continue with the same algorithm. I pop SB in red from the queue, and that makes me extend B. Again, I have A, and I have C. A reminder that the heuristic scores are not additive. So SBA has the same heuristic score as SA. That'll be important in a moment. Okay. Now I have the following new paths. I have SBA, and I have SBC. SBA has a path of heuristic score of 50. SA has a heuristic score of 50, and SBC and SC also. Both of them have a heuristic score of 7. And now it's time to sort the agenda. Because best first, we add everything to the agenda, and then we sort it. Now, a crucial detail, at least in the way that we do, or we implement search algorithms here in 6034, is that we break ties lexicographically, which means the following order is what's going to come out in the in the queue. Let's see. SBC, SC, SA, SBA. Here, SPC and SC, as I said earlier, they will both have a heuristic score of 7. But SB, B comes before C and SC, which means SBC is the one that goes first on the queue. Let me just add the note. Break ties lexicographically. Important. And this tie was broken the same way, just that A comes before B. It's a, you just align them and you sort by alphabetical order, basically. But we're calling it lexicographical because it includes other types of characters as well. Okay. Finally, we continue. We extend C because that's the one that's going to be popped from the queue. Goes down to M. So now we have SPC M. And because M has a heuristic score of 0, it's the one to go to the top of the agenda. Reminder, we need to pop this from the agenda, and then we try to extend M, but it's the goal node, which means we're done. And this is our answer. And that does it for best first search. Let's now turn our attention to the last of the heuristics-based search algorithms, and that's going to be beam search. Beam search is, to contrast with hill climbing, it's BFS-like. And to see how it is BFS-like, let's go back to the table that we've been referring to throughout this recitation. There we are. Now, going back to the maze example at the very, very beginning of this recitation, where beam search, by following a breadth first search, if I go back to the example with the fork of the road, I'm going to want to figure out what other forks are there, or how many more forks are there going to be at the end of each of the 2 corridors that I'm now faced with, as opposed to going down all the way on one, coming back and going down all the way on the other one. And that translates to adding things to the back of the queue, which I can BFS, no surprise, but I like the use of imagery, and it also keeps me, it helps me remember all the names to think of it in terms of the maze and the corridors. Now, the main difference, again, between BFS and Beam is that we're using a heuristic. But there's also another key difference, and here Beam is different from hill climbing and best first because there is a limit on the size of the agenda. And as you may know, Beam usually is accompanied by a constant. We're calling it W, that's the width of the beam, and that just says how many extended paths are we going to keep after sorting, and then to add to the agenda. There's no sorting of the agenda per se. And the cost function can be a heuristic or it can be something else. In this recitation, I'm equating the cost function to the heuristic. And as a final point, this one is going to remain missing. And it's because, as you'll see more visually when we do the example, beam search ends up eliminating some of the paths from the agenda, or from the queue. Sorry, I keep calling it agenda. It's force of habit from prior years. And the main drawback of eliminating paths from the queue is you might end up eliminating the shortest path or the only path to the goal inadvertently. So let's go through the example. Allow me to set it up here. Okay. Let's start with S. And you might remember, I'll switch back quickly. I've been using the number to indicate the evaluation, but because this is breadth first or breadth first approach, I'm actually extending everything at a level before moving to the next one. And I'll show you how I illustrate it. Whoops. Wrong color. Okay, so I have these three paths, which means I have the following. This is before adding to the queue. I'm going to write them in red, or I'm going to write them in green because they're not in the queue, and I don't want to mix red, which I've been using so far for other things on the queue. I have SA, SB, and SC, and I'll just rewrite the heuristic scores on the side. What's going to happen is we're going to sort these by heuristic score, which means I'm going to end up with the following: SB, SC, SA. And now we take into account the beam width, this W term. And what that says, W equal to 2, is that we're going to take the top two new paths, and those we're going to add to the queue. So we have SB, and the next one I'm also going to write in red, SC. And I'll explain why shortly. Let me erase this thing so that I can continue drawing. The way we illustrate, and I highly recommend that you follow this notation, it makes grading your work much, much easier, and keeping track of where you might have done a mistake, at least personally, is we've eliminated SA. Therefore, this path is this path is never going to be extended, at least not with this algorithm. So draw a red cross. You can draw it here, you can draw it on A itself. I typically draw it under because it's never going to go further than A. Okay? And now we extend both B and C. That's why SB and SC are both red. So B extends over to A and C. C extends to B and M. Again, with heuristic scores, 50, 7, 4, and 0. And again, we have to sort. I'm not going to draw it out explicitly. I'm just going to write out the top two. Reminder that this is why it's convenient that heuristic scores are per node and they're not additive. So I can just read off that SCM and SCB are going to be the ones that end up on the agenda. Now, if I extend all of them, let's say I could have extended A, C, B, but in reality, when I'm going through all of them, I'm eventually going to end up extending M. So this is where I finish. And because this is the path that I found, as we've been doing so far, make sure to circle it to make sure that to highlight that that's your final answer. And we actually don't even need this fourth step because the algorithm terminates there. And that is beam search. To finish off with the optimal search methods, I would like to work through an example of branch and bound with an extended set with the Shire and Mordor problem that we've been using this recitation, and at the same time, in the same fashion that we've been doing with the previous searches, let's fill out the table with all the search algorithms, but fill it out for all the optimal searches more or less at the same time. And the reason we can do that relatively easily is because they're all based on branch and bound. I mean, in branch and bound, you add an extended set, that's another one. Heuristic, you add another one. When you add them both, you get A star. So I think it's easiest to begin thinking about branch and bound in terms of best first search, because the main difference, best first, just to recap, is you extend the paths, you add them to the agenda, and then you sort the entire agenda by heuristic score of each path. In branch and bound, it's exactly the same thing, except you sort by path length. So we have an X here for sorting the agenda. I'm just going to add the note that it's by length, not by heuristic. Then I'll just add the little parenthesis here that it's by heuristic. Needless to say, all the other variations of branch and bound employ the same method. So all of these four search algorithms rely on length, sorting by length, and these last two sort by length and heuristic. I forgot to point these two. So let me make this a little bit more proper and visual. Length, I'm going to use L and H for length plus heuristic because it's getting crowded. Now, because we're relying on lengths for the first time, path lengths, we require edge weights. So this entire row needs to be checked off. And for the last two, we also need heuristics. There's no size limit on the agenda. It's not similar to Beam in that way. But there is a cost function. In the case of branch and bound with heuristic and A star, you could say there are two cost functions. But let's say there's only one. Now at the very bottom, because we're working with path lengths, we are guaranteed to find the shortest path. And reminder that best first sorts the entire agenda by heuristic. So eventually if there is a path, it'll find one because it'll keep trudging through all the paths. But because we're sorting by length this time, you're guaranteed to find the shortest path. And you could say in best first, yes, if it runs indefinitely, eventually it'll find the shortest path, but we're assuming that the program terminates as soon as it finds a path from S, or from your start node to your goal node. In the case of branch and bound, the first path that it finds is going to be the optimal one. That's the guarantee that we're doing with these first two boxes. Now these two, the next two, yes, they guarantee it, but with the caveat that I mentioned at the very, very beginning of the recitation with the tree of different optimal versus non-optimal blind informed searches, because branch and bound with heuristic is only guaranteed to find the shortest path if it is admissible. If the heuristic is admissible, that is. And A star is even stricter. A star will only guarantee you the shortest path when the heuristic is consistent. And eventually they'll keep exploring all paths until it either finds a valid path or you run out of paths. So if a path exists, these algorithms will find it. And with that, we can go back. And we can start working on extending this tree. Okay. We start with S, as with all the other search algorithms. We extend to ABC. And this time, I'm going to use yellow because I'm going to be working with path lengths. Notice that we've worked enough with heuristics, so I'm only going to use path lengths for branch and bound. I'm not going to do branch and bound with heuristics. This is 1, path length of 1, path length of 7, path length of 10. Okay. Let's add these to the queue. And once they are added to the queue, we sort them. So we get first SB, SC. Whoops. I still have it in my head that SA is too high, that SA is equal to 50. I tricked myself into thinking that I was working with heuristics again. No. So SA is the first one because it has a path length of 1. SB is second, SC is third. Okay, that means we're going to extend A. We're extending. This is B and M. And we add we add SAB and SAM to the queue, and we sort everything again by path length. So the first one is going to be SAB. Oops, forgot to add the path lengths. 4 and 101. Notice that unlike heuristics, which are relative only to the node that you're on, path lengths are additive. That's an important distinction to keep in mind. So this is SAB. SB, SC, and SAM. Again, the path under SAB is the winner in this case. So I'll extend B down to C with a path length of 8. And this is where things get interesting. So so far I've been doing branch and bound because I neglected to update the extended set. My apologies. I'll correct it now. Thankfully I've been using the numbers. I'll use the pointer to explain. So the first thing I did was I expanded S. Correct? So that means when I expanded it, S was added to my extended set. That was a step that I was missing. Afterward, A was expanded here, which means A went to my extended set. Then B was expanded and added to my extended set. And now I'm going to sort the queue according to include the new path SBC, and I'm going to get the following. SB, because SB just has a path length of 7, SABC, pardon me, SC, and SAM. It's a little bit cramped. Okay, so what does this tell me, this SB? Well, this tells me I need to go to node B, or to the path SB, at which point I would expand B to find its child nodes. But when I'm doing this, remember this is branch and bound with extended set, which means it remembers here, it remembers which nodes already have been extended. So when I go up here and I try to expand B, I actually skip it. When it's popped off the agenda, it sees that B has already been extended and it's skipped entirely. So the way we illustrate on paper that the path has been truncated is with this squiggly red or whatever line right under the node, because that means that node expansion has been truncated because there was, at least in the context of branch and bound with extended set, because it's already on the extended set. So in reality, what happens in step number 4 is SABC becomes the first one in line. So we extend C. I'm going to add the number on the other side to M, and the total path length is now 18. And now we run into a similar situation as in step 3.5 or 3 asterisk. Actually, I like the 3.5 prospect. Never mind. So rewriting sorting the queue, have a C. Again, I forgot to add it to the queue. Be very diligent about adding to the the extended set. SC, S, A, B, C, M. This is very current. Then SAM. And now as it happens, SC is popped off the queue. I go to SC and I see, that's a lot of C. And I see that C is already in my extended set. So I draw a squiggly line under C, and that path extension is skipped entirely. And then SABCM becomes the first path in line, followed by SAM. This one is popped off the queue, so I evaluate 5, and 5 being the 5th path extension, or the 5th evaluation. B and C were skipped altogether, which is why they didn't receive a number, they just received the squiggly. And because this is my final answer, or again, the extended set, because I evaluated M, it goes on to my extended set, and evaluating M implies that I realize this is the goal node, so this is my final answer. Just make sure you're more diligent than I am about updating your extended set. And that is branch and bound extended set. So the very last thing that I want to cover today, and I promise this is the very last thing, is how to combine path length and heuristics into a search algorithm. More specifically, I want to give you a simple example of A* so that you can try it on your own on the Middle Earth graph problem. So here I've opened up an extended set. I'm going to be more diligent about it this time. I have the queue initialized with S, and so we're just going to jump straight in. First, I extend S, and I'm going to start the notation right out with S. So at S we have a heuristic of 0. If you remember, I was using blue for heuristic, and I haven't gone anywhere, so I have a path length of 0. So that's the notation I'm going to be using when working with both heuristic and path length at the same time. With that out of the way, I extend over to A and to B. For A, I have a path length of 1, or a heuristics first, my bad. I have a heuristic of 100. For B, I have a heuristic score of 0. I'll add the pluses. Now I have a path length of 1 for A, and a path length of also 1 for B. And now remember that A* is a variation of branch and bound, and when we did branch and bound with extended set in the previous example, remember that we first get all the extensions, we add them to the queue, and then we sort, much like best first. So now I have my new extensions. Of course, SB is going to be first with a score of 1. And then SA with a score of 101. S from the previous step, and now as I evaluate 2, or I evaluate B as number 2, B joins the extended set. And B extends now to C, which has a heuristic score of 0 plus a heuristic score, or a path length of 10, but remember that path lengths are additive, so it's not 10, it's 0 plus 1 plus 10. So now we're up to a path length of 11. And again, we add the new path to the queue, and we sort the entire queue. Because SA was so outrageously large, now we have S, B, C, and SA still at the bottom. For the next step, again, I evaluate C, which adds it to the extended set. And C now branches into either one of A or G, which is the goal node in this case. A again has a heuristic score of 100, but now this time it has a different path length because we're further down the path. Now it has a path length of 0 plus 1 plus 11, that's 12. Whoops, my bad, it was additive already. It would be 11 plus whatever the path length from A to C is, which would make it 12. Now let's do the same for G. G has a heuristic score of 0 because it's the goal node, plus a distance or a path length of 100 plus whatever C had already, so it's 111. And now finally, we add these to the queue, and we have SA with a score of 101, S, B, C, and G with a score of 111, and S, B, C, A. Okay, so this problem continues on, and the reason I add this, I'm not going to finish it because it's getting cluttered and I've already exceeded the hour of a recitation, is a good exercise is for you to finish it. I already showed you how to work with an extended set, and I've just shown you the mechanism for working with heuristics plus path length. So you already have all the tools that you need in order to complete this problem. I'll just add those 3 dots right there. I encourage you to verify the heuristics, the admissibility, and consistency of this particular map. And then as extra practice, I encourage you to try A* on your own without any sort of help on the Middle Earth problem. And again, practice your consistency of heuristics and admissibility tests. And with that, you have all the tools that you need. And if you're enrolled in the course, you have access to all the resources that you need in order to really master the search algorithms that we cover here in 6034 and show thorough understanding of a very, very fundamental building block of artificial intelligence. As always, you're more than welcome in lecture and office hours and on Piazza to ask questions, to reach out to the staff with any questions, doubts, concerns. And we're happy to assist you any way we can.